All right, let's look at the Simpson's rule. All right, so Simpson's rule is essentially a method to approximate the value of the definite integral, pretending that the given curve is a quadratic function or a parabola. All right, so since Simpson's rule works on two sections at a time, n must be even. So whenever you use a Simpson's rule, n must be even. Right, and it's got this kind of a strange formula. It says Simpson's rule, S sub n is equal to 1/3 times. So you have f of x1 with the 1 coefficient, 1 as a coefficient, 4 f of x1, 2 f of x2, 4 f of x3. So you can see that first one is 1, but it goes 4, 2, 4, 2, 4, 2, keep on going until the next two to the last one, 4 f of x n minus 1, and then you have a 1 f of x n, then multiply by delta x. All right, so let's try to derive this. All right, so we have, so we want to approximate the integral from a to b f of x dx. All right, so we are trying to approximate this by Simpson's rule S sub n. All right, so this is what we're going to do. All right, so we're going to pretend that the given curve is a parabola. So let's say the parabola that goes through this point. So make sure that it goes through these 3 points right here. So let's say we're going to fit the curve going through these 3 points and then draw a parabola. Say parabola might look something like that, right? So we're going to pretend that this is a parabola. You can see that which is, parabola is pretty darn close to the original curve. All right, then we can find the area of the first 2 sections. We can approximate this first 2 sections using the formula we just derived, area under a parabola. All right, so let's do that. So the area there can be found by, we're going to put the 1/3. Right, so remember the formula here. So we do put the first value is f of x0. Next one, 4 f of x1 plus f of x2. Right, times h. H is exactly the same thing as delta x. So this is h. So delta x is going to be h. Right, so I'm going to use delta x here. Right, so that takes care of the first 2 sections. All right, now we're going to do the same thing. So we're going to use try to make sure to go through these and pretend that this is a parabola. Right, then we want to find the area there using exactly the same formula. Right, so the next one is going to have, so I'm just using the same formula. You have a 1/3. Then the leftmost number is f of x2. Then you have a 4 times f of x3. And then you have a f of x4 and times delta x. Right? So you can keep on doing this. So keep on doing the same thing up until you hit the very last one. So here's the very last one. So you have, I'm going to go through those 3 points. And then you have a parabola which might look kind of like that. Then we find the area under the parabola instead of the original one. So the last one is going to be same formula 1/3. And the leftmost number is f of xn minus 2. Next one is 4 times f of xn minus 1. And then last one is f of xn times delta x. Right? So you can see that we can simplify this since everyone seems to have 1/3 here and 1/3 here and 1/3 there. So we can pull out 1/3, right? Then also we have every single term has delta x at the end. We can just put delta x at the end, right? Then we have, so we're going to put f of x0 plus 4 times f of x1. Then you can see that there's overlap. F of x2 shows up twice. So you have a 2 times f of x2. Next one is 4 times f of x3. And next one is, f of x4 shows up twice. So 2 times f of x4. And so on. And the last one is, I'm going to just put the two of them because so 4 times f of xn minus 1 plus f of xn. Barely made it in there. All right. So that's the formula we got here. So this is called Simpson's rule. So it's essentially using the parabola to approximate the area under the graph.